Okay, welcome to part B of this linear multiple regression. And as you can see, I have picked up one example, a sample data, which has been produced from scratch. It's not a real data that I have taken from any source. What it says, it has certain values like fasting blood sugar, FBS, age, survival index, blood pressure, and weight. So this medical data is related to a set of people uh, across the ages and for various levels of fasting blood sugar, which is typically measured in um, mg per deciliter. So anything around 100 or below is considered to be normal, and above 100 is considered to be type 2 diabetes. So this is about the FBS, which is a fasting blood sugar, abbreviation for fasting blood sugar, the age, whether the patient is having blood pressure or not. If the patient is a BP patient, it is the value is 1, otherwise it is 0, and weight of the patient. So the survival index reflects in case of a specific disease or an infection, what is the possibility of the survival of the patient considering the blood sugar, age, BP, and weight. So these are all the various dependent variables, and survival index, independent variables, and survival index here is the dependent variable. In our case, in part A, it was x1, right? Either we say y or x1. Now there is a, what is it that we are supposed to do from this? So this is the data set of another set of people whose blood sugar level and age and the status of blood pressure and weights are mentioned. Based on the data from the first set, we have to find out the survival index of the uh, patients of the second set. So you can think of a scenario where a particular kind of a disease spreads in a city, locality, or a country, and we have data of the patients, and when the disease revisits, say after 10 years or 20 years or 100 years, we want to correlate and see what is the survival index of the possibility of the survival of the patient based on the data that we already have. So basically it is um, it's a kind of a use of a predictive model using linear multiple regression. So we will be predicting the value of dependent variable based on the linear multiple regression model, and what is it that we will cover in this discussion, what will not cover in the discussion. So let me clarify. So we are not going to discuss the model selection here, or whether the estimates are biased or unbiased. We are not going to interpret the p-values for variables in the regression model. So what basically we will be discussing is the one which I showed in part A, the multiple linear regression model. We will use that model to build or to plot a graph in R, or to plot the regression model in R, and to predict the values. And regression, basically regression analysis or regression model consists of a set of machine learning methods that allow us to predict a continuous outcome variable based on the value of one or multiple predictor variables. So the linear regression coefficients are determined so that the error in predicting the outcome value is minimized, And this method of computing the beta coefficients, which we've already seen, is called the ordinary least squares method. And when you have multiple predictor variables like x1, x2, the regression equation can be written as y is equal to b0 plus b1 into x1 plus b2 into x2. This is what we saw in the previous section, right? I'm not going to uh, reiterate those things once again or repeat those things. One thing which I wanted to tell you here is in some situations there might be an interaction effect between some predictors. So this is an interesting thing, and we'll see in this as an example. So it means that increasing the value of a predictor variable x2 may increase the effectiveness of the predictor x3 in explaining the variation in the outcome variable. So it means that if x2 and x3 uh, helps in the prediction of x1, then there may be some association between x2 and x3, so that if we increase the predictor variable x2, that may help or may increase the effectiveness of the predictor x3 in explaining the variation in the outcome variable. So this is an interaction effect, and the other one is the normal additive model, which we discussed in part A. So we will see both these examples, and there are a few things which we will not be definitely will not be discussing in. So this could be in some cases the relationship between the outcome and the predictor variables is not always linear also. So in these situations we need to build a non-linear regression such as the polynomial or spline regression, and which we are not discussing in this example. One interesting thing and one important thing that we will definitely visit in this example is the best model. So what is the best model which is defined in a linear regression model? So the model which has the lowest prediction error is the most popular model, and the most popular metrics for comparing the regression models are ideally root mean squared error and adjusted R square. So we will see what root mean squared error means and what adjusted R square means. So the definition is like root mean squared error, or RMSE we say, measures the model prediction error. It corresponds to the average difference between the observed known values of the outcome and the predicted value by the model. So lower the RMSE, the better is the model. So that is one criteria. Another criteria is the adjusted R square. The adjusted R square basically it represents the proportion of variation or information in the data explained by the model, and which corresponds to the overall quality of the model. The higher the adjusted R2, the better the model. So for RMSE, the root mean squared error, the lower the better. Adjusted R square, the higher the better. Fine. So we will go to R, and we will build this data set and try to plot it and try to predict the values for these targeted patients. What is the survival index of these targeted patients based on the value from this, right? Let us go to R. So as I said, to start with some basics, multiple regression with no interaction, which we saw last time, is x1 is equal to b0 plus b1 x2 and b2 x plus b2 multiplied by x. So here b0 is the intercept, and b1 is what we saw last time, the coefficient of partial regression coefficient, that is b1 on 2 keeping 3 fixed, and the other one is b2 is b1 on 3 keeping 2 fixed. So the same thing which we saw here. So this is the above equation, as I said, is known as additive model, because here we are not seeing any effect of x1 and x3, association of x2 and x3, or the relation between x2 and x3 in predicting x1. So we are saying that x2 is independently predicting x1, and x3 is again independently predicting x1. That means when we are considering x2, we are assuming x3 as fixed, and when we are considering x3, we are assuming x2 as fixed. But in the real scenario, this may not be, and we will see when to take this as a correct model, additive model, or when to take the interaction as the right model. So multiple regression with interaction is this. So this is what is the interaction between x1 and x2, and there is another coefficient that comes in this. So when to use the additive model and when to use this interaction model, we'll just briefly we'll see with this example. Fine. This particular solution that I have done here requires certain packages. As you can see, caret, you got to install this package caret, tdverse, and include the libraries of tdverse and caret, and of course you need the other three important libraries, ggplot2, ggigraph, and ggigraph extra. So these are the three packages you first need to install and then include in the libraries. Fine. As you can see, first I am reading the patient's data, the one which we have for historical purpose, and the steps what normally we do is we basically divide the data, the full historical data, into two parts. That's a real life scenario I'm trying to explain you. Since the data that we have is very small, so we may not do this way, but actual the real life, the general practice is you divide the whole patient's data into 80:20 ratio. So 80% you feed in the model to decide which model you should use, and then use that another 20% of the data to test the performance of that model and find out the error and the R squared that we discussed just few minutes before. So this is pretty simple. We are reading this in the patient's data frame, and next we are using sorry, we are reading the other one, the outcome or the data set to be predicted also in another variable called predictor data. So we have two variables, and just to test whether we have picked the right data or not. So let us see. Okay, I have not run this inclusions, so let me run the libraries first. Okay, I thought of avoiding the typing and demonstrating this example as it takes time, so I've already tested this so that we save time on the stuffs. So let me this I'm sure I have this data package of this package is already installed. In any case, just okay. So let me read this. So this is the patient's data, the same data which we saw. This is the patient's data. This is the first 6 data that we are displaying for the sake of checking whether we have the data correctly loaded in our array or not. And this is the one which we have to find out the survival index, which is shown as not available, and we have to predict the survival index data here. Now, as I said, we will be using the caret library to call this function create data partition. So we will partition the data into 80:20, so that the train data or the training data will be 80% and the test data will be 20%. So you can go ahead and run this. So this particularly It divides the whole data set into two. One is the training data and the test data. If you want to see the test data, you can see. So we have the same data that we have divided into test and training, and this is the train data that we have. So 80% of the data. Now what we will do is we will build the model using the train data with 80% of the data. So this is the syntax which is used. Important thing here is we are using the additive model, not the interaction. So right now we are saying that the fasting blood sugar and age are two independent variables which have no association between themselves, but each of these decide or impact the dependent variable survival index. So what is it that we are going to build here? We are trying to build a linear regression model where survival index is dependent on fasting blood sugar and age, and we will see how good that model is. So let us run this. So once you run this and you run the summary, you see that you have a set of values here, which is what we discussed about the this is the residual error that we discussed in our last video. This is the adjusted R squared. So we're not going to discuss the p-value here because my whole idea is to show you how to plot this in R. So for the other values I will talk in my linear regression analysis section, not in this video. So in any case, we have the coefficients of this model as this we will use to build the graph, to plot the model in R. And now we have already built the model, and we will do a prediction on the test data, the 20% of data, right? So let us do this on the test data. Okay, so this is what it says. This is the prediction on the 20% of the data. And the interesting thing is, if you want to predict, now since you have built your predictions here, if you want to predict the any values which I showed you here, this is the one for the predict data. If you remember, this is the target audience on which we want to predict, for which we want to predict their survival index. So we can feed this prediction, and we can now this is either you can write this way, or alternatively you can write in this way, whichever method or syntax you are comfortable with. So I'm running this one. So what you can see here is basically it is running the predictions. It is using a predict function, and it is running the model 1, which we actually built here on the target data, right? So if you run it, so this is the outcome, and we can predict it. This is the way we predict. No, either you can do this, or so this is how the problem with my mouse, which is hanging. Okay, so see, so the first patient that we saw has a survival chance or probability of 91.4%. The other patient with the given data has a survival index of 89.93, and so on. So we can predict the survival index of the patients based on the data set or based on historical data in real life. So far it is fine, but we want to see what is this is the error which we already discussed. So what is the error in the model? So if you see the error in the model, and to run this error in the model, I am running only on the test data. Okay, so that is the approach, because in real life you will have a huge set of the input data, where even a 20% of data will be good enough to run on the test. So I see that my RMSE is 0.062, my error is 0.062, and my R squared value is 0.6344004. So these two are the values that I will compare when I run the interaction model. Now let us go and build the interaction model now. So if you see, this is the interaction model. The only difference in the syntax is this particular syntax here. Instead of plus, it's a star. So it says the survival index is dependent, obviously dependent on the fasting blood sugar and age, but fasting blood sugar and age are also associated with each other, and an increase or decrease of the one of these actually helps the other variable in predicting the dependent variable survival index. So this is the syntax. It is a repeat of the same thing, except this change in the syntax, and we do a summary model. We get the summary values, the coefficients and other stuffs. Now we will see what is the error in this particular model. Now here also, based on this, you can predict. It is the same thing. If you want to predict, you can predict, you can run the predictions the way we ran it here. Same thing you can do here as well. Everything is same. Okay, so let us see what is the do you remember what was the error and this in the first model? Okay, we'll find it out. So in the second model, the error is 0.0618. We will have to see what was the error in the first model. In the first model was 0.062499. Here it is 0.061. So I think this is a more realistic model in terms of the error. It is slightly less, and R square value is 0.639573. What was there in the first case? First case 0.6344, and here it is 6395. So obviously this is more. So in this case, the interaction model is more meaningful. That means there is definitely an association between the blood sugar level, the fasting blood sugar level, and age in determining the survival index of the patient. So this is the overall thing I wanted to show you in the predictions. Now we will go and plot each of these. So in the first case, if you see, we will use the additive model first, the simple model. So this is what we did, but now we will run for all the patients, for the input one, not the targeted patients, because for the targeted patients we wanted to find out the survival index, and we have already found it in both the cases. Now we will plot the regression model, a linear regression model graph for the linear regression model. We will plot a static as well as an interactive graph in R, and we'll see how it looks like. So this is what it is. We are running for all the patients, and instead of the test data here, because it makes sense, we want for all the patients. This is the model name is FIT1, and these are the coefficients. I'm interested in coefficient of FIT1. So these are the coefficients. If you see, these are the coefficients of the model, the additive model. This is the intercept. This is the coefficient for fasting blood sugar. This is the coefficient for age. So it shows there's clear trends. It's a negative sign, shows that with an increase in the fasting blood sugar and with an increase in age, the survival index goes down. So the person definitely has a lesser chance of survival with a higher blood sugar and a higher age. So that's the general trend that it shows. But we need to see a more interesting picture through the graph. And if you have the background of regression analysis, then fine. Otherwise, this is just to explain you. Now, if I use a simple static graph, how do I find out the values of the various coefficients and intercepts? So this is the equation. I mean, if you remember, we already discussed this last time in part A. In part A, we did not discuss the interaction model, but that's fine. You will understand easily now. So this is the one we already discussed in part A, coefficient of FBS. This is nothing but B 1 on 2 keeping 3 fixed, and this is B 1 on 3 keeping 2 fixed. So which is already discussed last time. Coefficient of partial regression, right? So here x1 is a survival index, which is the dependent variable. X2 is the fasting blood sugar. X3 is the age. X2 and X3 are the independent variables. So x1 is equal to intercept plus coefficient of fasting blood sugar multiplied by x2 plus coefficient of age multiplied by x3. So if this is the equation, then we find out x1 as this. This is important to understand because we will use this to plot the regression model. Now x1 is equal to, this is the same thing, the arrangement. So x1 is equal to intercept plus coefficient of age into x3 plus, because here we have a fixed value of x3. Here we have two variables, sugar level and age. Age is x3. So what we are saying is that for a particular age group, what is the x1 equation? What is the survival index for a particular age group with a varying blood sugar level? So that is what it says. So that is why it says for a fixed value of x3. So for a fixed value of x3, only thing that is a variable in this equation is your x1 and x2. So these two, if you see, these two makes the intercept value here, and all the subsequent values in the same column, and these two and this one makes the slope. So this is the regression analysis. You can go through this once again. It's not at all difficult. It's very simple. Do not get overwhelmed with this. And the one which I used below is nothing, just a table. You can use anything. If you are comfortable with the data frame, you use data frame, that's fine. So I have used a table with the same calculation. So for each age groups, so for age 30, 40, 50, 60, 70, 80, I have various intercepts and the various slopes. So I have put it in a table. So let me run it. So it's not difficult. Do not get scared with this. You can try your own, and there are various ways of doing it. You know, some uses functions. I know you can use a function, you can use table, you can use data frame, whatever is comfortable for you. So now I will run this and plot. Once I plot, you will be able to appreciate what I mean to say. So as you can see, this is the graph that this particular regression analysis model builds, and we have used this calculation which I just explained you. This is the calculation, and I put these values in the table. This is a pretty simple calculation. You can go through this and you will understand. It's not at all difficult, and based on this we have built this linear regression model, and it's a linear multiple regression model. So if you see this plot, let me enlarge it. You have this is the FPS and the blood sugar, fasting blood sugar level on the x-axis, and we have not given the labels, and also you can put labels and other stuffs in this graph, that's fine. And this is the survival index. So this and these are the regression lines for particular age group. So this is fixed for age 30, this is for 40, this is for 50, 60, 70 and 80. So we have taken a table with 30, 40, so these number of rows. So it clearly shows that for a higher age group, the same and with the same blood sugar level, the chances of survival are less. And for a lower age group, if you are young and if you have the same blood sugar level, the chances of survival are more. So this is the way you can plot this predictive model using multiple linear regression. But there is another very interesting and good method where you do not have to do this regression analysis calculations, and that is the reason I asked you to install this libraries, ggiraf and ggiraf extra. There is a function available in these packages called ggpredict, and this is a very handy and very interesting function where it will plot an interactive graph. So let me run it and show you this particular. You don't have to do any calculation as such. As you can see, this is the ggpredict, a function that generates this interactive plot. This is interesting, as let me enhance it a bit. So the same thing which we did using the linear regression analysis and the calculations using the table, it is for the same. It is the same thing, but prepared in a nicer way, where you don't have to do any calculation as such. This is the model for age 20, this is for age 40, this is for age 60, and this is for age 80, and the results are indicating the same thing, that for a higher age the survival index is low for the same level of fasting blood sugar. So this is pretty interesting, and you can use this particular interactive plot to find out, let us say you have a requirement to find out what is the survival index for a person age 60 with a fasting blood sugar of say 165, which is not there in our input data set. So you can find the corresponding y-axis value, and you can use last time I showed you how to find out the corresponding y-axis value in my previous videos, and there are many methods, and you can find out that yes, the survival chance of that person is between 0.8 to 0.9, and you can find out the exact percentage. So this is the additive model using interactive plot. We will now use the interaction model using the interactive plot and as well as the normal plot. Now for the interaction model, it means that there is an interaction between the sugar level and the weight. Now we are here in this, for this example I am taking a more realistic example. So it is it's a common notion that the weight is related to the fasting blood sugar level of a person. It may not be medically correct, but statistically, based on the data that we have, it looks like that it is related, because it has all variations of age with the different levels of blood sugar. So having age with the blood sugar makes no sense with the kind of data we have. So again, it depends on what kind of data you have with you, that is important. So as a quantitative analyst, as a statistician, you first have to decide what is it that you're exactly trying to find out. So in this case, I'm trying to find out an interaction model of linear multiple regression to find out the survival index based on the variables, independent variables, the fasting blood sugar and weight, which are also having association between them. So they are associated with each other. So let us run this. So now the syntax is star instead of plus, and let us do the summary. So we get all these values here, which we had in our previous case also. The calculation is slightly different for regression analysis here. So if you see this coefficient of the fit2 model, this is the model named fit2. So these are the intercept. This is for FBS, the fasting blood sugar is for weight, and this is FBS and weight. So here this is an interesting number. So this is something which you have to be a bit careful if you are trying to find out the regression analysis. Again, it is not very difficult. It is again requires just careful attention. In this case, we are saying x1, the survival index, is dependent on x2 and x3 like in the past case, but only thing is here, this is the equation. There is another value that comes in the equation, is this, the joint coefficient of fasting blood sugar and weight, or coefficient of fasting blood sugar and weight. So here if you see this equation, x1 is the y-axis, which we have to determine. It's the dependent variable here, and what we are trying to do is, for a fixed weight of a person with a varying blood sugar level, we are trying to find out. So weight we have taken here as a fix, like in the past we have taken the previous example, age we have taken fixed. So weight is x3. So if I take x3 as fixed, then my equation translates to this. So x1 is intercept plus coefficient of weight multiplied by x3, and then this whole term, the first term, because x3 we are taking we are taking one regression model graph for one weight. So for a person who has a weight of 60, this is one intercept. For a person who has weight of 80, this is the one intercept. Similarly, for the same person, this is the slope, right? And here is the table that I have defined using the same equation. So weight, for weight 60, this is the intercept. The first part is the intercept. The second column of the first row is the slope, and like that for each of the weight. I mean, if you want for other weight, so you can put for any weight. Now if you want to find out for a weight of 63, which is not there in our data set, so you can always do and find out and predict the value. So it is simple. I have just put it as an example to show you how you can do this, and this is a manual method. So we will again use a interesting predict function without manual intervention, and I'll show you. So let us run this manual method first. So I have to check, there is some problem with this. Okay, not a problem. So we got this value. So this is the table we generated. I can show you, just 1 minute. Don't worry about these warnings. This is the table we generated using the calculation. So I have done the calculation in the table itself, so that's the advantage of taking table. Now if you plot the same thing what we did last time for editing model, and we will do the same thing for the interaction model. So this is the graph that we generated using the manual method for the interaction between two independent variables, something which we saw for the additive model as well. So this is the graph. Now let me now make it big. And so this is an interesting graph. If you see, each of the colors here represent the weight, if you see the color I've given, I've converted into a categorical variable, the factor. So each of the color is represents a weight. So this is the regression model for weight 60, this is for 80, and this is for 90. So this has an interesting perspective. Now the same thing, if you want to run it using the GG predict as we ran it last time, you don't need such calculations and you can quickly find out the values. This is the syntax to run GG predict to build a plot of the interaction model. So the syntax remains same, only the model we have changed now. We have used fit2 instead of fit1. So this is very interesting here. If you see, this is an interactive plot, so you can see some interesting results here. So for weight 60, you can see that for the patient with the age 60, when you compare it for the patient with age, let us say for a person with weight, this is the next one, 70. So for the so if there is a higher blood sugar level, then the person with weight 60 has a higher chance of survival. That's interesting. Now you can check with the data. So this is happening around the value 250. So above 250 fasting blood sugar level, person with, if you see the same blood sugar level for weight 60 and between age 70 to age weight, not age. So person of weight 70 with a sugar level of 300 has more chances of survival than person of weight 60, and whereas before this point, the situation is just the reverse. So this is an interesting phenomenon, and since these regression lines are not parallel, so it does establish a connection between the fasting blood sugar and the weight of the person in determining the survival index. So if you keep one variable, increasing one variable actually helps in predicting the outcome in a different in a proportional manner. So this is the logic of interaction model. So this is how you can plot multiple linear regression models in R using various kind of methods which I showed you, using either regression analysis and the static methods, or using the GG predict, which is already an available function, and it depends on exactly what and how you want to find it out. And again, you also saw how to predict the outcome of a variable based on input data sets, so input variable. So thanks for watching this video, and hope to see you in the next video again. Thank you.